All right, so today we're going to be talking about IRT, but we're going to throw in a little bit of EFA real quick. So IRT kind of requires you, well, for the purpose of this assignment, you wanted us to check for unidimensionality, and the way I know how to do that is using EFA. So I'm going to bounce around in the syntax a bit. We're going to load in the library, read Excel, and push the data into IRT. And we're actually not going to use that ever. Huh. Oh, well, it's there. But we want to essentially kind of clean the data. There are 19 different variables in here. We have sex, male, female, and a bunch of different measures of organizational justice, distributive, procedural, and I justice. Forget what that one is, but I'm not doing that one, so super not important. So we're going to do distributive justice, and basically we're going to create a data frame of the 4 distributive justice items. So DJ 1, 2, 3, and 4. Don't really care about 5 right now. And so this is going to just pretty much give us the 4 that we want separate from the 19. And so we're going to be using IRT trim. So we're going to push it into IRT trim. This section actually does IRT stuff, but we want to essentially check the unidimensionality assumption. In order to do this, we have to do EFA, so that's what this stuff is down below. So we're going to create a correlation matrix for the 4 variables, which pretty much just looks at if the items are correlated with each other. And we're going to run a KMO test, the Kaiser-Meyer-Olkin test, to see if our data is adequate to actually run EFA. So this whole big chunk here just creates the function KMO, and it actually allows us to run it because it's not a native function to R. So when we actually run KMO, we get this neat little section here. So we get an overall statistic and a report printed out and some other stuff. So basically what we care about is this report. The KMO test yields a degree of common variance meritorious. So basically our data is good. If we had a smaller sample size than 399, we may have been in trouble, but for all intents and purposes, our data is good to use. The degree of common variance is acceptable. The next test is the Bartlett test. Where did I put that at? So we're going to test the correlation matrix to make sure it's not an identity matrix. So we want to see that there are relationships between the variables, but we want to make sure that they are not all exactly the same. So the Bartlett test is this section down here. It's a chi-square test, and our p-value is super duper significant. Also gives the degrees of freedom. And so basically, our Bartlett test is significant. Our KMO tells us that we're good to go. We also want to check and make sure we don't have a multicollinearity problem. So we do a determination. We check the determinant of our correlation matrix. So if it's smaller than 0.001, we may have a multicollinearity problem, but we don't, so that's good. So that's what that function does. So those are testing the assumptions of EFA. Actually running it is this section down here. So we're going to get some eigenvalues, and we're going to get it scree plot. So we're going to run EFA, factor analysis. The data set that we want to use is the EFA matrix, and we want 4 factors because we have 4 items. We're not going to use a rotation yet because we may not need to rotate it. We only rotate it if the data is fucky. And the factoring method we want to use is multiple likelihood. So when we run that, we get, where is it? This down here. So basically this tells us our factor loadings. So these are the eigenvalues for our 4 factors, and they all load onto one factor, which is fantastic. We have unidimensionality. That's what we wanted. But if you like pretty scatter plots, ooh-wee, or scree plots, ooh-wee, that's a good one. Look at that, showing us one factor. Look at that sexy elbow right there. Ooh-wee. So we have one factor, and now we can go on with the actual IRT, which is scrolling up here. So scrolling down just to make sure everything lines up. Okay, so we want to get the library that allows us to run IRT. Then we want to actually get the graded response model estimates for the 4 variables that we chose. So each of these is an item with a bunch of observations from the item. And we're going to use those to create some curvy charts, some item response curves and item information curves. So the first one down here, plot model down here, this gives us our 4 item response category characteristic curves. So that's dit1, 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 and dit1. So each of those slightly changes, but their overall shapes remain largely the same. So this is for item 1, and each of these colored lines represents strongly disagree, somewhat disagree, neither agree nor disagree, somewhat agree, and strongly agree. And so each of these curves represents the likelihood, because we are using Likert scale data rather than correct or incorrect. So each one of these essentially represents the likelihood that a person who is high or low in perceived distributive justice will select strongly disagree to strongly agree. So if you think of this bottom axis instead of ability, think of it as perceived procedural justice. Someone who is low, who's like -4 in the theta for perceived distributive justice, will be super likely, like 100% of the time, choose strongly disagree on the item 1. Someone who is super high in it will choose strongly agree. So when we ran the model back here, we got a bunch of coefficients printed out. And this, the extremity 1, 2, 3, and 4 are our intercepts, also known as the B parameters. And the discrimination here are the slopes. Those are our A parameters. So for our item 1, each of these, -2.151, that's this intercept. Extremity 2 is this intercept. Extremity 3 is this intercept. And wait, 2 to 3, 3 to 4. Yeah, so extremity 2 is -0.869. Extremity 3 is -0.468. And extremity 4 is 1.159. So all 4 of these intercepts correspond with these right here. So our B parameter is the item location. It's basically the halfway point between the maximum and minimum C parameter, where the slope is maximized. So this is like the maximum point in the slope, because it's kind of hard to, because they're not straight lines, the slope changes. So the slope here is different from the slope here and here. So it's basically where the slope is maximized. And while normally these can be viewed as difficulty when the answers have a correct and incorrect option, since we have Likert scale data, we use it as a likelihood of scoring in a certain direction when distributive justice is high or low. So the probability that someone who is -2, when you just think about it like that, on distributive justice is like kind of 50-50 that they'll either score a 1 or a 2, because that's where the intercept is between those two. So it's kind of iffy. But if you were to go a little bit higher, for example, the probability that they would score somewhat, they would check, not score, sorry, they would check off somewhat disagree increases, while the probability that they would check strongly disagree decreases as you get closer to 0 or neutral. And it's interesting to note that the essentially center point of these curves is not directly over 0. It's kind of skewed a little bit on the negative end. So they are more likely overall to, if they are feeling neutral, or even, they're more likely, if they are kind of in the middle, to go and report that they are feeling negative more so than positive. I think I'm explaining that correct. So that's what the B parameters are. The A parameter is the slope, and that's this value here. And that is that's weird. It's the degree that the item discriminates between people on different regions of the continuum. So people feeling low on distributive justice have a smaller chance of choosing 5, while people high on distributive justice have people low on distributive justice have a smaller chance of choosing 5 than the people feeling high on distributive justice. So it's kind of what I was mentioning before. So it's the overall slope of that. Next we go, and so these are all kind of following the same logic. Next we go to the item information curves, and that's pretty much the last portion. It doesn't have corresponding coefficients, but essentially the item information curve tells us how much of the information each item gives you at specific levels of theta. So for the most part, like I was mentioning before, most of the information that is explained happens at the lower end of theta. So we got a lot of peaks at -2 and maybe like -0.75. And each one of these lines represents one of the items. So we have 4 items, so we have 4 lines. But if you notice, the red line, distributed justice item 2, is lower. So it explains less information, and it basically explains less information than the other 2 items, and it is difficult discriminating between, it has more difficulty discriminating between differences in higher and lower, explaining information for different levels of theta. So its curves aren't as pronounced as the other ones. So these have much more prevalent dips. They're all dipping kind of in the same place, but the amount of information explained is significantly different between, I don't know if I can actually say that, is different, visibly different between items 1, 3, and 4 and item 2. So that is IRT in R. So yeah, that's about it. Bye.